Hey guys, this is Mr. Lee with a video regarding Chapter 3. So in Chapter 3, we're going to look at examining relationships. So now we're going to go to bivariate data, so two variable data. So in the past, what we've been studying is just one variable data. So when we're plotting things like histograms, or even if we're going with bar graphs, depending on whether we have categorical or quantitative data, in the past, we were just looking at univariate data. So when we graphed it, the value of the data went on the x-axis, or the category if it was categorical. And then on the y-axis, the height of the graph was just simply the frequency or the relative frequency. And then we studied that special graph called the ogive, which is the cumulative density, the cumulative relative frequency graph. So we're on the left, everything is a percentile. So now we're going to look at bivariate data. So we now have an x, and we're going to plot one of the variables on the x-axis and one of the variables on the y-axis. And before we just start plotting, it's really important that we distinguish between which one should go on the x and which one should go on the y. So let's get started. So we have three sections in Chapter 3. In Section 1, we have scatterplots and correlation. Section 2, we're going to learn about the least squares regression model. And in Section 3, that's a typo. That should say 3.3. We're going to learn about correlation and regression wisdom. So that is just some pointers and some things to look out for when we're using correlation and linear regression. So in section 3.1, our goals are to figure out how to identify explanatory and response variables, how to construct scatter plots to display the relationship between that explanatory and response variable, how to then read a scatter plot and interpret the data that we see, how to measure the linear association using what's called Pearson's R, or the correlation, and then also how to interpret what that correlation is telling us in the context of whatever real life situation we're in. So in real life, it's nice to examine one variable, but in many cases, we want to look at the relationship between two variables. And we're going to distinguish between these two variables. One is going to be what's called an explanatory variable, from the word explain. It kind of explains the relationship. And the other is going to be called the response variable. And it kind of responds to, this variable sort of responds to the explanatory variable. So in Algebra 1, you guys learned about independent and dependent variables. And the independent variable is a lot like, in statistics, the explanatory variable. And so that we're going to plot on the x-axis. And the dependent variable in Algebra 1 was the thing that depended upon the independent variable. And so likewise, in statistics, the response variable is going to get plotted on the y-axis. It is the variable that responds to the change in the x variable, or the explanatory variable. So most statistical studies look at the relationships between bivariate data, or even more than bivariate data, multivariate data. Okay, but in this course, we're not going to do too much on multiple regression. We're going to stick with linear regression, so two variables. Okay, so in AP statistics, you have to understand and know how to work with univariate data, so one variable data, and bivariate data. And we're not really going to worry too much about multivariate data in this course. That's for future courses when you get to college. Okay, so the response variable measures the outcome of a study. An explanatory variable may help explain or influence changes in a response variable. Now, in this first sentence, a response variable measures the outcome of a study. Recall that in Chapter 1, we learned that there are generally, broadly, there are two different types of study in statistics. The first is an observational study. And the second is an experiment, a randomized experiment. So with this particular model what we're learning, linear regression, the relationship between two variables, sometimes the study could be an experiment, and sometimes the results of the study could be coming from an observational study. So it's actually really important that you know what kind of study was designed and where the data came from. So in statistics, you never want to just start crunching numbers and just like plugging numbers into the computer. You want to really understand and examine how the study was conducted and how the study was designed, and does it meet all the criterion for an actual randomized experiment, or is it merely an observational study? The reason for that is because if it's from an observational study, we cannot conclude any type of causal link between the x variable and the y variable. We don't know, we can't even, not only can we not assume, but we can't even imply that there is any causation when the bivariate data was a result of an observational study. However, on the other hand, if the study was a legitimate randomized experiment, then there actually is a causal relationship between the x and the y variables. Okay, so in many studies, the goal is to show that changes in one or more explanatory variables actually cause. So that is, if we're talking about cause, if the study is designed to create a causal link between the explanatory and the response variable, then it's a randomized experiment, okay? But most of the time, not most of the time, but a great deal of the time, you're going to get data that is only from an observational study, and so you cannot even imply that there's a causal link between the x and the y variable. So be very careful with that, especially on your assessments and on the AP exam. Okay, so the graph that you need to know for bivariate data is a scatter plot. Okay, and a scatter plot is exactly what it sounds like. Your explanatory variable is going to go on the x-axis, your response variable is going to go on the y-axis, and you're going to have bivariate or paired data. So just like you learned in Algebra 1 and you did in geometry, right? Each point on your two-dimensional graph, each point will have, it's an ordered pair of coordinates, an x-coordinate and a y-coordinate. So each dot on the scatter plot represents a relationship between, or a measurement, an actual value of an explanatory variable and its corresponding response variable value. Okay, and it looks exactly what it sounds like, scatter plot. It looks like a scatter of dots sort of all over just this coordinate plane. So here's how to make a scatter plot. Okay, so to make a scatter plot, what you want to do is first you have to examine and think about which one of these two variables is the explanatory variable. That needs to go on the x-axis, right? And so here's a little hint that the authors give you. The explanatory variable goes on the x-axis. Make sure that you label and scale your axes. That is plural, right? Your x and your y axis. Because now in this case, on the y, you're not just going to label it frequency or relative frequency. You're going to label the y axis with the response variable. You also need to put a title to your graph. And that is one thing that on the homework, that is not something that I'm looking, that closely for on your homework. But on your quizzes, tests, and on the AP exam, is that going to be an important thing for points? You betcha. I can't tell you, I can't stress enough, all of you are brilliant scholars and you're capable of getting, A pluses in this course and a 5 on the AP exam. But it's these kind of things that make the difference between a 5 and a 4 or a 4 and a 3 on the AP exam. These little details are critically important, and they are, as I can tell you from my experience as an AP reader, these are like bolded on the rubric that every AP reader has. Okay, so this is a very important point. Anytime you're making your graph, label and scale your axes. And then finally, you're just going to plot the individual data values that you receive. You'll probably get a table of data, and each datum will have, an X and a Y value. And so now in your calculator, instead of just making stat edit and editing one list, you're going to have two lists. And it's important that the order is the same in list one and list two, okay, because this is paired data. Okay, so here's an example of a scatter plot. Okay, so in this particular case, and this is an example out of the textbook where we have, what do we have? We have 1, 2, 3, 4, 5, 6, 7, 8. And I don't remember the exact context, but we have something like 8 students going, to school, and we look at the relationship between the student's body weight and the weight of what the weight of the backpack that they are carrying. Okay, so since body weight is our explanatory variable, it goes on the x-axis. So before we even plot this data, and I know the scatter plot's right here, but what kind of relationship do you think that we would expect to have? So as body weight increases, do you think that backpack weight would increase or decrease? Well, if there is a correlation between these two things, if there's a strong correlation, we would probably just sort of intuitively guess that as body weight increases, then probably backpack weight would also increase. Okay? And that's the kind of thing that we're looking for when we're looking for a relationship between two variables. Okay? And then each one of these, this is paired data. So this 120 and 26, these go together. This is the X value and the Y value of a student who weighs 120 pounds and whose backpack weighs 26 pounds. Okay, and then where is that? Well, that datum is right here. Okay, it's right here. That dot is right here, 120, 26. So each one of these red dots represents the paired data. So for example, this dot over here is the student who weighs a little bit more than 155, and then whose backpack weighs a little bit, kind of between 30 and 32 pounds. So maybe 158. So where is that on the table? Right here, 158.31. So now when you look at this scatter plot and you look at these dots, do they have some kind of shape? Like, do they create some kind of geometric shape? And really the most important shape, the one shape that we're looking for, is a line. We're looking for a linear relationship between your x and your y variable, your explanatory and your response variable. There are other types of relationships that are important that we can study in statistics, but in our course, the only relationship that we're going to be studying is a linear relationship. Okay, we're going to be using what's called the linear regression model. Okay, so body weight is our explanatory variable. It goes on the x-axis. Backpack weight is our response variable. It responds to the body weight, so it goes on the y-axis. And then finally, like for example, this student who weighs 120 pounds and has a backpack weight of 26 pounds, that is represented by that dot right there. Okay, so now you also have to know how to interpret a scatter plot. So to interpret a scatter plot, follow the basic strategy of data analysis from chapters 1 and 2. Look for patterns and then important departures from those patterns. So before you get into the nitty-gritty of examining a scatter plot, first look at the entire scatter plot and look for an overall pattern and look for any major departures from the overall pattern. And make sure that you mention those as your opening statement of examining or interpreting a scatter plot. Okay, so here are the steps to examine a scatter plot. And it's going to be direction, form, strength, and outliers. Just like in the past in univariate data, when we were describing a distribution of univariate data, we talked about what? Shape, center, spread, and outliers. Now with bivariate data, we're going to talk about direction, form, strength, and outliers. So as in any graph, before you talk about the direction or form or strength or outliers, look for overall patterns. Look for the overall pattern of all of the dots, and then any dots that really depart from the overall pattern. Okay. And then you want to describe the overall pattern of the scatter plot by talking specifically about the direction, form, strength, and outliers. Okay, so here we have that scatter plot again. And where is the direction, form, strength, and outliers? Okay, so a summary sentence for direction, form, and strength is that there is a moderately strong, positive, linear relationship between body weight and pack weight. Okay, so for direction, there's really only two directions that we're looking for, either a positive association or a negative association. With a positive association, as x increases, y also increases. So the shape, the overall shape is that the dots are moving upward to the right, Okay, so if you think of this, if you think of this in terms of Algebra 1 and geometry, if you think of the slope of the line, the slope is going to be positively sloped. Okay. The other direction that we're looking at is the negative direction. Okay. And think about, like in Algebra 1, what did that look like? It looked like a negative slope. Okay. So if these dots generally were going downwards, okay, that would be a negative direction. So another way to think about that is as x increases, y decreases. As the explanatory variable increases in value, the response variable decreases in value. That would be negative. Okay. Now, in this particular case, we have a positive relationship, a positive association. Okay. You can see that the dots are generally going upward as we move to the right. Strength. Strength is talking about how strong is that relationship of the dots to our model, okay, to some kind of model. Now, here's the tricky part, okay? It could be very strong and nonlinear, okay? So for example, if we had some kind of an exponential curve here, okay, and the dots sat right on that exponential curve, that would be considered a strong relationship. Okay, but in this case, what we're talking about is, because it's a linear relationship, we're talking about, well, how strong are the dots to the linear relationship? Okay, how close are all of these dots to this line, to this, and you may have studied in Algebra 2 or in pre-calculus the line of best fit, or the best fit line. Like, how close are these dots to the best fit line? So, and that really is form. There's really just two forms that we're looking for, and that is linear or curved. Linear or curved. Okay. So with linear, obviously, that's what we are hoping for, because what we're doing in this course in AP Stats is linear regression. We're not going to be doing nonlinear regression. There are going to be nonlinear data that's presented to you, and we're going to transform that data to straighten it out to make it more linear. Okay. So with form, your two options are linear or curved. With direction, it's positive or negative. With strength, there's moderately strong, strong, moderately weak, and weak. Okay, and that is just how close the dots are to the predicted model, whether it's curved or linear. In this case, the model is linear because we already stated that there is a positive linear relationship. Okay, so strength in this case is modifying how strong is the linear relationship. Okay, oh, I skipped over this other uh, interpretation. It appears that lighter students are carrying lighter backpacks. Okay, so what about these dots? What about these dots? So this is an SAT example from page 144. This does not correlate to your textbook. This is actually from TPS 4E. But I believe that we also have this same example of the SAT results, right? So, looking at different schools, they looked at, well, the percentage of students in that school that took the SAT versus, and they plotted that against the students' mean math score, right? And what do we see? What kind of relationship do we see? What about the strength, direction, and form? What about direction, form, strength, and outliers? Okay, what do we see? Um, Direction, is this positive or negative? Well, clearly it's flowing in a negative direction. Okay, it's flowing in a negative direction. Okay, but is it linear? No, it's not. Okay, it goes. It's almost like there's. If you were to draw lines of best fit, it almost like there's a line that goes this way, then a line that goes this way, then a line that goes this way. So it's not linear. It's curved. It's pretty strongly curved. Okay. And do most of the dots line up with the overall curved pattern? Yeah, they pretty much do describe that curved pattern really does describe this data very well. So in this case, you would say that there's a moderately strong negative curved relationship between the percent of students in a state who take the SAT and the mean SAT math score. So let's just think about that. Okay, let's just think about that for a second. What does that really mean? That means that for states that require their students to take the SAT, their mean math score tends to be lower, okay, than these states over here that there's a very small proportion of students that are taking the SAT, but their mean math score is very high. Now, do we know why that is? No, we don't know why. The data does not tell you why that is. And we don't attempt, as statisticians, we don't attempt to explain why. There may be many factors to why this relationship exists. But when we're interpreting bivariate data, we're not really, as part of our interpretation, we're not stating why we think that that relationship is the way it is. All we're doing is we're stating what we know about the relationship, what the data shows, like what relationship that the data shows. Okay. Now, outside of interpreting data, we could speculate on why that is, but our speculation would never be part of our interpretation. And if I were just to, just kind of speculate, I would think that, well, the reason why, as the percent taking the SAT goes up, the mean math score goes down is because a lot of these students probably don't even want to take the SAT. They're probably just being required by their schools to take the SAT. Okay. And that is true. When I was at a private school teaching AP statistics, we forced all of our students who took an AP class, we didn't give them a choice. They had to take that AP exam for that class. And overall, you would probably see a pattern like this, whereas schools that don't require their students to take the AP exam, they could take the AP course, but they could opt out. They would probably have overall, higher results because only the students who are really motivated and are going to study, and probably perform well are going to opt into taking the AP exam in this case. Okay. All right, here's one other thing that we didn't talk about yet that's very important with interpreting scatter plots. You also want to look at what are called clusters. Okay, so there are two distinct clusters. Notice that there's a very strong, tight cluster up here where there's a very low percentage and very high mean math scores. And then there's another distinct cluster over here, okay, with very high percent taking the SAT and very low mean math scores, right? So there are really two distinct clusters. So if there are clusters like this, you always have to mention that when you're interpreting a scatter plot. Okay. In the previous example, there were no clusters. Okay. And then are there any points that really kind of catch your interest because they depart from the overall pattern? Well, yeah, here's a point right here. Okay, so here is a state that has a very low participation rate of percent taking the SAT, and their mean math score is very, very low. Okay, so this kind of deviates from this cluster. And here's another point right here, which just the mean math score is much lower than what we would expect based on the rest of the data. Okay. So there are two possible outliers. All right. So now what we want to do is we want to measure how strong is the linear association. And a linear association specifically is called correlation. Okay. There's bivariate data can be associated in any way, right? You could have an exponential association. You could have some type of like parabolic association. But when the association between bivariate data is linear, then you're specifically going to call that correlation. So association is a general term that just shows there's some kind of relationship, some kind of mathematically predictable relationship between two variables. But correlation specifically means that the association is mathematically linear. Okay. So a scatter plot displays the strength, direction, and form of the relationship between two quantitative variables. Linear relationships are important because a straight line is a simple pattern that is quite common. Unfortunately, our eyes are not good judges of how strong a linear relationship is. Like so far, what we said, well, there's definitely, our eyes are picking up that, yeah, there's definitely some kind of linear relationship, but how strong is it? All we could say is moderately strong. Well, now we have a mathematical way of measuring exactly how strong the linear relationship is. Okay, can you think about what kind of mathematical model, like what kind of elements would that mathematical model have in it? Well, it turns out that departures from the expectation, dots that depart from the expected sort of linear relationship, okay, they have a little bit of deviation, what we call deviation with univariate data. But with bivariate data, we're going to call this, there's some error there, right? There's some space between these dots and the line. And it could be that the best line of fit, it could be that the best line of fit actually never even touches any of the actual data values. Okay. So here is the formula for measuring how strong the linear relationship is. Okay. And it is called the correlation, which is lowercase r. Make sure you use lowercase r because capital R means something totally different. So the correlation R measures the strength of the linear relationship between two quantitative variables. And you're going to call this, you can call this just the correlation coefficient. Your textbook, your authors are going to refer to this R as the correlation coefficient. In other textbooks, they call it Pearson's correlation coefficient after the statistician who came up with this nice equation. But here we go. So here are some things that you need to know about R, the correlation coefficient R. R is a number between and including -1 and 1. Okay, so R is between and including -1 and 1. So when R is greater than 0, so when R is positive, it indicates that the association is positive. Okay. What did positive mean? It meant as X increases, Y also increases. Okay. When R is negative, it indicates that there's a negative association. As x increases, y decreases. Notice that I'm not just saying, oh, the slope of the line is positive or the slope of the line is negative. Okay. Why am I not saying that? Because on the AP exam, I've seen in the past more than once where there's a multiple choice question that says, well, interpret what, a positive R means. And what you have to say is that as x increases, and state what the actual x is. Okay, in our first example, as the student's body weight increases, the backpack weight also increases. That's how you interpret a positive association in a context of a problem. Values of R that are near zero, they're close to zero, whether they're negative or positive, as those values get close to zero, that indicates a very weak linear relationship. Well, what does very weak mean? It means that the dots are quite far from the line of best fit. The strength of the linear relationship increases as R moves out away from zero towards -1 or towards 1. Okay. So, and -1 and 1 are kind of the limits. So if R equals -1, that means that the negative relationship is extremely strong. Like all the dots would line up on a negatively sloped line. Okay. It doesn't mean that the slope has to be -1 of the line, though. Okay. Don't think of R as the slope. R is not the slope. Okay. R is not the slope. Okay. So don't think of it as the slope. Okay. But if R equals 1, positive 1, that means that you're going to have a positive association between an x and y. And how strong is that positive correlation? That positive correlation is so strong that all of the dots line up exactly on the line of best fit. So those extreme values only occur in the case of a perfect linear relationship, which how often do you think that happens in the real world? Pretty rarely. Okay, so here's some different correlations. Okay, so look at this. Look at these dots. Okay, what is the overall pattern of these dots? Well, I don't know. It kind of looks like there's a negative association, but there also kind of appears to be a positive association. So there's a zero correlation here. Okay, we don't know whether there's positive or negative, or it's impossible to tell. Here's a correlation of -0.3. So overall, the dots have a negative relationship, negative association, but they're not that tight to a line. Okay, this line would be very, very wide, so it's not very tight. Here's a stronger relationship in the positive direction, so R equals 0.5. Okay, so going in this direction. Here's a very strong relationship in the negative direction where R equals -0.7. And then here is an extremely strong positive association where R equals 0.9. And here's the strongest of all where R equals -0.99. Now, if I covered up all of these correlations, okay, R equals 0, R equals -0.3, okay, and I just showed you the scatter plots, and I gave you a list of correlations. Could you match up the correlation to the diagram? Well, you better be able to, because that is a very, very common quiz, test, and AP exam question. So how do we actually calculate the correlation coefficient R? Fortunately, I'm not going to make you do this by hand ever, not even once, okay? But when you look at this beautiful formula that I inserted using free software, and so it's kind of pixelated, but when you look at this beautiful formula that someone discovered, what does it look a lot like? Well, we have this R equals 1 over n minus 1. Where have we seen 1 over n minus 1 before? That's some kind of adjusted average, right? You remember where we saw that? Standard deviation. And if you look at all of these, okay, this looks a lot like standard deviation. Well, how far away is x from the mean of the x's? Okay, and then it's adjusted by dividing by the standard deviation of x. And then you have the same thing with the y. You multiply these, so you have a weighted sort of average. So how far is the y away from the mean of the y's divided by or adjusted by dividing by the standard deviation of the y's? So now, because we have bivariate data, there's an x bar and a y bar. And if there's an x bar, there's also an sx. And when there's a y bar, there's also an sy. So you're never going to need to do this by hand. You're just simply going to use your calculator. Okay, but this equation, hopefully you're seeing that this looks a lot like the equation for standard deviation. Okay, so here's some very important facts about correlation. Okay, how correlation behaves is more important than the details of the formula. In fact, this formula, don't even memorize it. Don't even write it in your notes. You're never going to need to use it. All you need to know about the formula is that it's some kind of average, adjusted average, and it's very similar to like looking at the standard deviation of x and looking at the standard deviation of y. Okay, and you're kind of combining those two things. Math purists, sorry, we're not going to go into the derivation of the formula. Okay, so here's some important facts that you need to know. Correlation makes no distinction between explanatory and response variables. So if you were to rotate, if you chose the wrong x and y variable, or when you're calculating the correlation coefficient r, if you put in L2 for L1 and L1 for L2, doesn't matter. Okay, correlation simply measures how tight the relationship between the x and the y is in a linear relationship. Okay. Next, r does not change when we change the units of measurement of x or y or both. And changing units of measurement is very important because, as you saw in the last chapter and even in chapter 1, we like to do transformations of data. And we are going to be doing transformations of data when we're doing linear correlation, linear regression, excuse me, because sometimes the data is actually going to be nonlinear, and then we're going to transform it and make it linear. 3, the correlation coefficient r itself has no unit of measurement. Here's some things to be careful of. Correlation requires that both variables be quantitative. Your x and your y variable, they both have to be quantitative. Next, correlation does not describe curved relationships between variables, no matter how strong. Why is that? Because remember how we defined correlation. Correlation is the measure of the linear association between two variables. Only the linear association. Okay? Correlation is not resistant. Okay, so just like mean, just like standard deviation, R is strongly affected by a few outlying observations. Well, why is that? Well, now we can refer to the formula of correlation. What does R depend on? Well, R depends on the mean and the standard deviation. The mean and the standard deviation, ... the mean and the standard deviation. So since the mean and the standard deviation are not resistant, well, correlation is not resistant at all because it's composed of the mean and the standard deviation. And finally, correlation is not a complete summary of two variable data, not at all. It's only one component. Okay, when we talked about direction, form, strength, and outliers, correlation, you could think of it as just a measure of strength. So you're not, it's not a complete in and of itself interpretation or examination of bivariate data. It really only speaks to the strength of the linear association. So here's some practice. So for each graph, Can you go ahead and just ballpark what you think the correlation R is and interpret it in context? Okay, so that's very important to be able to interpret it in the context of the problem. Okay, so now what do we have? On the x-axis, we have the boats, the number of boats registered in the state of Florida. The unit of measurement is thousands. So here we have 400 represents 400,000 boats that are registered in the state of Florida. 800 would represent 800,000 boats registered in the state of Florida. And then on the y-axis, the response variable is the number of manatees that is killed by boats every year. Okay, the number of manatees. And if you don't know what a manatee is an awesome, pretty cool looking creature. Kind of looks sort of like an elephant, but lives underwater. Okay, lives most of its life underwater. So as the number of boats registered in the state of Florida increases, what do we see? Well, the number of manatees killed by boats also increases. Well, that makes sense because more boats in the water, more propellers, more, accidents, more boat drivers running over manatees. Okay, so can we estimate what the correlation coefficient R would be? Well, direction forms strength and outliers. Direction, positive. Strength, strong. Sorry, that's my dog, obviously. Form, linear. Any outliers or clusters? Not really. Not really. Overall, not really any clusters. Okay. Outliers, not really. There's some low values here, but not, so strikingly low that we would consider those outliers. Okay. So what would you guess? What would you ballpark R is? Is it going to be positive or negative? Well, obviously it's going to be positive. And is it close to 1? Yes, it's pretty close to 1. So maybe you might guess that R equals 0.9. And interpret it in context. Here's your interpretation. As the number of boats registered in the state of Florida increases, the number of manatees killed by boats also increases. That's your interpretation in context. All right, next. Correlation and interpreted in context. Direction. Direction is positive. Form. It's pretty linear. Strength. Somewhat strong, maybe moderately, somewhat strong. Maybe you could say somewhat weak. Okay. Now, let's actually just ballpark, like how strong do you think R is? I'd say maybe R is equal to about, I don't know, what do you think? I'd say maybe 0.5. And now let's interpret it in context. Let's interpret the R in context. Well, as the number of storms predicted increases, the number of storms observed also increases. Okay, but because R is equal to 0.5, the correlation between storms predicted and storms observed is not very strong. All right, next, can we estimate the correlation R and interpret it in context? Well, this one is pretty hard to, this does not look like a very strong linear relationship at all. It almost looks like it goes, kind of this way, but also kind of this way. So R, I would say, is very weak, maybe something like 0.2. Okay, and what does that mean in context? That means that there's a very weak positive linear association between healing rate of limb 1 and the healing rate of limb 2. All right, now how about this one? I couldn't tell you whether R is positive or negative. So I would say that R equals 0. There is a very weak unpredictable, there's almost no correlation. And maybe we wouldn't say exactly zero, but if we said R equals zero, that would mean that there's no strength to the correlation between last year's percent return and this year's percent return. All right, so in summary, a scatter plot displays a relationship between two quantitative variables. The explanatory variable may help explain, predict, or cause, if it's a randomized experiment, changes in a response variable. And when examining a scatter plot, look for direction, form, strength, and outliers. Also, make sure that you talk about clusters. When you're talking about outliers, also look for clusters. And then finally, the correlation coefficient R measures the strength and direction of only the linear relationship between those two quantitative variables. That's it for now. Enjoy your homework, and next we'll talk about 3.2. In 3.2, we're going to learn about least squares regression and how to use the LSRL, or what's called least squares regression line. Okay, and again, the line is a model, okay, because notice that the model doesn't fit all the data. Okay, so it is a model. It's a mathematical model that we're using. And we use this in the real world for prediction. Okay, and we're going to tell you exactly like how to craft your answers or how to state your answers when it comes to prediction. Then we're going to look at what are called residuals and residual plots. Okay, residual was that little error that I talked about of how far the dots are away from the best fit line. And then we're going to look at R squared, not just R, the correlation coefficient, but now we're going to look at R squared. Okay, and it has a very important role when it comes to regression. And then in section 3, we're going to talk about correlation and regression wisdom. Thanks, guys. Have a great rest of your day. Post any questions you have in the discussion board.